let us discuss about the calculation of packing efficiency of the crystal. After that, imperfections in the solids. And the third topic in this session is going to discuss is the properties of the solids compounds. Now, let us move to calculation of packing efficiency of unit cells. Packing efficiency means the fraction of total spheres occupied in the unit cell. If more spheres are occupied and less spaces are present, then packing efficiency of that crystal is more. So, how this packing efficiency is calculated? Let us see. Packing efficiency calculation in simple cubic. Simple cubic crystal. I am taking simple cubic crystal. This is the edge length of my crystal. Here, at corners only they are present. Spheres are present at corners. Here these two spheres makes an edge. Remember that two spheres makes an edge in the simple cubic. Packing efficiency is calculated by this formula. It is equal to number of spheres occupied by total volume of unit cell into 100. This is the formula used to calculate the packing efficiency. In simple cubic unit cell, number of spheres occupied is equal to number of atoms per unit cell and its volume. Sphere volume is 4/3 pi r cube. Z into 4/3 pi r cube by total volume of the unit cell is edge length cube multiplied with 100. So, for simple cubic Z is 1, 4/3 pi r cube we know edge length consists of two radius. So, edge length is equal to 2r. So, instead of a cube, write 2r whole cube into 100. Therefore, 4/3 pi r cube by 8 into r cube into 100. R cube cancelled. So, pi by 6 into 100. This is nearly 52% of packing efficiency is present. So, for simple cubic 52% of spheres are present and the rest 48% is vacant space. 48% is vacant. Let us calculate the packing efficiency of body centered cubic lattice, BCC. Let us calculate the packing efficiency of BCC crystal. As I already said that packing efficiency is equal to volume occupied by all spheres by total volume of unit cell into 100. This is the packing efficiency formula. Now, I am drawing the BCC crystal structure. In BCC, where the spheres are present? At corners and at body center. Corners also we have different crystal structures. In this crystal, this is my point A, B, C, D, E, F, G and H. At this area, one more sphere, here one more sphere is present, and rest of the corners also present. So, from this corner to this corner, it is a body diagonal of a cube. So, in the body diagonal, especially in BCC, the nearest atoms are present in the body diagonal. So, then this FB length is a body diagonal. Body diagonal length is FB. This is equal to 1R, this is equal to 2R, R, and this is another R. Total R, 4 radius. Body diagonal length FB is equal to 4 radius. And if you take the point from here to here, this is the edge length, it is A. From here to here, this is 2A. Now, we have this kind of triangle, F, B and D. This length is equal to 2A, this length is equal to A, and this is body diagonal length FB. According to Pythagoras theorem, FB is equal to root of 2A square plus A, that is equal to how much? Root of 3A square. Therefore, body diagonal FB is equal to 4R, that is equal to root of 3 into A. So, remember that body diagonal length is equal to root of 3 into a. This formula is very useful in calculating the numerical problems. Therefore, a is equal to body diagonal length by root 3, that is equal to 4r by root 3. We know in BCC crystal, number of atoms per unit cell are 2. Therefore, packing efficiency is equal to total all spheres are 2 and each sphere volume is 4/3 pi r cube by volume of the unit cell means you have to write 4r by root 3 whole cube into 100. This gives around 74%. Upon simplification, you will get 74%. So, when compared with the simple cubic, BCC packing efficiency is more. The white space, it is not 74, it is nearly you get 68%. Not 74, 68%. So, the packing efficiency of simple cubic is less, and in BCC the efficiency is improved. In the third case in FCC, it is around 74%. So, let us move on to calculation of packing efficiency of FCC. Let us calculate the packing efficiency of FCC or CCP. We know the packing efficiency is nothing but volume of all spheres by total volume of unit cell into 100. Let us have a cube. This is the edge length A. This is also edge length A. Here also at corners different spheres are present, and at face centers, face center means here. This is the face, its center is here, face center, and this is the corner, and this is the another corner. This is at face center. From here to here, it is face diagonal. Face diagonal, let me write like this. Say this is A, this is B, and this is C. This length is how much? This is a triangle. This length is A. From here to here, A. This AB is what? AB is face diagonal. That is equal to R, 2R, R, 4R. According to Pythagoras theorem, AB is equal to root of A square plus A square. So, AB is equal to root of 2A square, that is equal to root 2A. So, face diagonal consists of one complete sphere and two spheres of each half, total 4R, that is equal to root 2a. This particular formula is very useful in calculating the numerical problems. Face diagonal length root 2a, body diagonal length root of 3a. So, 4R is equal to root 2a. From this, a is equal to 4R by root 2. We got edge length here from this Pythagoras theorem. Now, in this face centered cubic lattice, effective number of atoms per unit cell are 4. So, packing efficiency is 4 spheres and each sphere volume is 4/3 pi r cube by total volume a cube means 4R by root 2 whole cube. Upon simplification, you will get 74% of occupancy of the spheres. Only 26% is vacant space, void space in FCC. So, among these three varieties of unit cells, FCC or CCP is a highly compact state, is a highly closed packed state, and the void space is very less. So, the metals which are having FCC and CCP are very hot and they are having high melting points. Let us move to the next topic, imperfections in the solids. Solids are having different number of spheres in a regular pattern of arrangement. If any pattern of arrangement is disturbed during the cooling of the crystal, then we will call it as imperfection or defect in the crystal. Let us see the number of types of different defects in the crystals. If you observe here, the crystal defects are mainly classified into point defects and line defects. Point defects, see here throughout the crystal is okay, but at here and here, due to the presence of another sphere which is unwanted here, or sometimes due to the vacancies some defects occurs, those are known as point defects. In the formation of certain crystals, throughout the line will be missed. Throughout the layer, a single dimensional layer is missing from the lattice point, which is known as line defects. In this chapter, mainly we will focus on the point defects. Point defects are stoichiometric defects. Again, stoichiometric defects are classified into vacancy defect, interstitial defect, Frankel defect and Schottky defect. All these are stoichiometric defects. And impurity defect, if any foreign element is present along with the crystal, then it is called impurity defect. And lastly, non-stoichiometric defects. They are of two types. When metal is in excess, metal excess defect, metal is deficient, metal deficiency defect. You have to remember that in the stoichiometric defects, the stoichiometry of the crystal will not disturb. That is very important point. Whereas in the non-stoichiometric defects, the total stoichiometry of the crystal will be affected. Let us know what is vacancy defect. Vacancy defect is one of stoichiometric defects or point defects. Here and here, the spheres was missed. In this point and in this point, there are no spheres. Then what happens to the crystal? Number of atoms per unit volume decreases. So, because of vacancy defect, density of the crystal, density will decrease. Especially this type of defect occurs in non-ionic crystals. If you see interstitial defect, here this row, this row, this row, these all 4 rows are perfect. But due to the occupation of additional sphere in the interstitial spaces, here, 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 proper arrangement will be disturbed. This kind of point defect is known as interstitial defect. Due to interstitial defect, what happens to the density of the crystal? Density of the crystal will increase because more number of atoms per unit volume. It is also shown by non-ionic crystals. Let us move on. Frankel and Schottky defects. In the Frankel defect, the defect arises due to displacement of spheres from their lattice points. That is called Frankel defect. Here, regular arrangement is minus, plus, minus, plus. This is no defect. There is no defect in it. In the second layer, up to here no defect, whereas one cation is displacing from its place and occupying this interstitial space. Total number of spheres in the unit cell remains constant. That is why no change in the density due to Frankel defect. This type of Frankel defect observed in the ionic crystals whose atomic sizes are small. Atomic sizes of small. If you observe the Schottky defect, in this Schottky defect, what is meant by Schottky defect? The defect arises due to missing of the atoms or ions from their lattice position. They will be missed. They will not find anywhere in the crystal. As a result of this, because of Schottky defect, the density of the crystal will decrease. In case of NaCl, out of 10 power 6 ions, almost a million ions, one ion gets missed. So, this Schottky defect is shown by crystals, ionic crystals, whose cationic sizes are bigger. AGBR is able to show both Schottky defect as well as Frankel defect. So, Schottky defect, Frankel defect, and these two are point defects, not line defects. Let us move on. Another type of point defects, that is impurity defect. If you observe the crystal lattice, total crystal is okay. structure is excellent. But due to the foreign element, suppose here I have taken strontium chloride. Little amount of strontium chloride is doped into more amount of sodium chloride, then what happens to C? Strontium ion is bigger ion and it is also having two positive charges. So, here one strontium ion will takes place the position of sodium ion. To compensate the valencies, for one strontium ion, two sodium ions should escape out from their lattice points, giving one point vacant. This type of defect is known as impurity defect. Let us see the non-stoichiometric defects. Non-stoichiometric defects is of two types: metal excess defect and metal deficiency defect. Here, let us see the metal excess defect. See, all this crystal is properly arranged. At one of this place, say at this corner, anion is anion is missed. A hole is formed in the place of this anion. Due to the missing of anion in the crystal, metal cations will be excess. The electron released from the anion will be occupied by the hole and forms an F center. So, what is F center? A vacant space in the crystal lattice when occupied with the unpaired free electron and it imparts color, that center is called F center. For example, in zinc oxide, Zn+2 cation and O-2 anions are present. In cold condition, it is white. When the zinc is heated, the oxygen comes out, oxide ion comes out as O2. So, O- ion place is vacant, in that electron is occupied forming F center. Due to the F center, in hot condition, ZnO will be in yellow. ZnO is cold in white condition, yellow in hot condition. Let us see the metal deficiency defect. Here, this is the crystal and this brown color sphere is say Fe+3. The green color balls are Fe+2 and the violet color balls are say O-2. So, in FeO structure, when the crystal is heated and it is suddenly is being cooled, then at one or two sides on the crystal lattice is occupied by some ferric ion. Because of +3 state, suppose one Fe+3 enters into the crystal. Here 2 Fe+3 was entered. So, how much positive charge will be excess? 6. So, by introducing 2 Fe+3 ions, 3 Fe+2 ions should be removed off. So, previously here and here Fe+2 ions was there. as Fe+3 ions enters, for 2 Fe+3 ions, one cationic vacancy occur. So, cationic vacancy is nothing but metal deficiency defect. So, this is observed in mainly in FeO type of crystals. Solids are best known for their conductance. So, let us see the properties of solids in the form of conductivity and in the form of magnetic behavior. The properties which explains about the conductivity are called electrical properties of solids, and here magnetic behavior is explained by magnetic properties of solids. We know in the nature substances or some substances conduct electricity, some substances doesn't conduct electricity, and some substances are conducting electricity in a medium manner. So, based on the conductance of the electricity, the solid substances are divided into conductors. The conductors have high conducting capacity. Semiconductors have poor conducting capacity. Why conductors have high conduction capacity? This can be explained on the basis of valency band and conduction band. Suppose metals are good conductors of heat and electricity. For insulators, take wood, they are non-conductors. Silicon, germanium, they are semiconductors. Pure semiconductor is known as intrinsic semiconductor. Pure semiconductor conducting ability is very poor. If any foreign substance is doped into it, the conduction capacity of semiconductor will be improved. So, let us see why metals are good conductors. You take silver, copper, gold, or you take sodium. Sodium metal is having different electrons in different energy levels. This is one sodium atom, this is another sodium atom, this is another sodium atom. Like this, in the metal, different sodium atoms are present and different energy levels are present. In the valency shell, that is in 3s1, sodium is having 1 electron in 3s1. Here also 1 electron, 1 electron. These are called electrons present in the valency shell. These electrons are said to have, they are present in valency band. The electrons present in the valency shell are said to be valency band. And inside, there are so many electrons in the atom. The valency electrons, while they are connected to any electrical source, the metal conducts electricity because the valence electrons moves from one place to another place and carries electricity as well as heat. So, this atom and this atom, see here the valency band is almost overlapped. For this you can explain like this. This is the valency band and this is the conduction band, almost overlap. There is no forbidden gap, that is why metals are good conductors. Whereas in insulators, there is a large gap, more than 3 electron volts gap is present between conduction band and this is valency band and this is conduction band, large gap. So, it is not possible to cross over this gap by the electrons, so that they are non-conductors, they cannot conduct electricity through them. Semiconductors, the energy gap between valency band and conduction band is intermediate to metals and insulators, so that their conducting ability is intermediate to them. The insulator's conducting ability is 10 power minus 10 to 10 power minus 20 ohms inverse meter inverse. Insulators have very less conducting ability. As already I said that semiconductors have poor conducting capacity, because there is a large gap between conduction band and valency band. The conducting ability of semiconductor can be improved by adding some dopant. So, due to doping of foreign substance, we will get 2 types of semiconductors. Pure semiconductor, which is known as intrinsic semiconductor. Impurities, depending upon the type of impurity added, the conductors, semiconductance can be classified into N type and P type semi impurity conductors. N stands for conductance due to negative ions, negative particles like electrons. P stands for the conductance through positive holes. When N type semiconductors are possible, when P type semiconductors are possible, let us see. Suppose silicon, it is having 1s2, 2s2, 2p6, 3p2. So, in the silicon valency shell, silicon belongs to group 14. It is having 1, 2, 3, 4 valency shell. This is another silicon atom. This is the 3rd silicon atom, 4th silicon atom. Due to the valency electrons, they form one bond, here one bond, here one bond, here one bond, here one bond. Here some other silicon atoms are also present. Group 15 elements like arsenic antimony is introduced at one of the place of silicon atom. Suppose here 50th group, here 50th group element is introduced instead of silicon, like 50th group element P. It is having how many valence electrons? P is having 1, 2, 3, 4 and 5. Silicon is having 4 valence electrons and 50 group elements are having 5 valence electrons. So, again here bond, here another bond, bond, bond. 4 bonds are taking place. Valence is fulfilled with 4 bonds. Still, this electron remains in the crystal due to this negative stands for N. Due to this electron, the conductivity of the semiconductor will be improved. This kind of the conductance in which conductivity takes place through negative electrons are known as N-type semiconductors. P-type semiconductors, how they are formed, let us see. Silicon atom, silicon atom, silicon atom, like this. Number of silicon atoms in the pure conductors, semiconductors. It is having 4 valence electrons. Now, silicon belongs to group 14. We are doping the semiconductor with group 13. Group 13 elements having only 3 valence electrons. Suppose here, if I introduce gallium, indium type of 13th group elements, then what happens, let us see. Suppose gallium is introduced. It is having only 1, 2, 3 valence electrons. This bond, this bond, this bond is okay. But previously, here if silicon atom is present, there was a bond. But gallium is having only 3 valence electrons. Here, only 1 unpaired electron is present on silicon, leaving a hole. When electricity is passed, the hole moves towards if the electron moves in one direction, the positive hole moves in its opposite direction. In this way, the conduction takes place through positive holes. So, this type of conductors are known as P-type semiconductors. These semiconductors are mainly used as diodes, NPN diodes, and they can be used in the photoelectrical conductors as ECs and so on and so forth. In this way, semiconductors are very useful in designing the computer chips, etc. So, let us move to the last topic, that is magnetic properties of solids. Based on the behavior of solids in the magnetic field, the solids are classified as paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic and ferrimagnetic. Let us see what are paramagnetic substances. They are weakly attracted by the magnetic field because of presence of one or more unpaired electrons. As number of unpaired electrons increases, paramagnetic behavior also increases. Example, O2 is having 2 unpaired electrons in their anti-bonding molecular orbitals. That is why O2 is a paramagnetic substance. And similarly, all transition metals belongs to this kind of magnetic property. Diamagnetic substances are repelled by the magnetic field This is because all the electrons are paired up. Examples of diamagnetic substances are benzene, NaCl, Zn+2, scandium+3, etc. Why they are repelled by the magnetic field? Here, this is a diamagnetic substance and this is a magnet. It is repelling with each other. This is because all the electrons are paired up like this. In diamagnetic substance, all electrons are paired up. Because of compensation of the alignments, they are repelled by the magnetic field. Ferromagnetic substances. Ferromagnetic substances have small domains of magnetic moments and they are all aligned in the same direction. So, what are ferromagnetic substances? The substances which are strongly attracted by the magnetic field. Even the magnetic field is removed, they attains the magnetic behavior. The ferromagnetism is because of alignment of domains of magnetic moments in the same direction. MnO is the example for antiferromagnetic substance. Last one is ferrimagnetic substance or ferrimagnetism. The term ferri comes from ferrites. Ferrites mainly contains Fe+3 ions. Example for ferrimagnetic substance is Fe3O4. Here, the magnetic moments alignment is not cancelled. They have parallel and anti-parallel magnetic moments which are not cancelled by each other. They are unequal. Unequal number of domains of magnetic moments are present in the ferrimagnetic substances. Example Fe3O4. In the solid state chemistry, some points are to be remembered forever. Those are solids are anisotropic. This point is remembered forever. And Bragg's equation, n lambda is equal to 2d sin theta. Calculation of density of the unit cell. Density is equal to number of atoms into m by Avogadro number into volume of the unit cell. That means D is equal to Zm by Avogadro number into A cube. Packing efficiency of any unit cell. Packing efficiency. What is the formula? Effective number of atoms per unit cell Z, and its spherical volume 4/3 pi r cube by total volume of the cube means edge cube, edge cube. So, packing efficiency is calculated like this, fraction, that is into 100. And in BCC, nearest atoms are observed at body diagonal, therefore, body diagonal length is equals to radius of 4 spheres. That will be equal to root of 3 into A. So, body diagonal length 4r is equal to root of 3 into A. And in FCC, face diagonal length 4r is equal to root 2 into a. From this you can calculate r, from this you can calculate a also. When come to the coordination numbers of simple cubic crystal 4, of FCC is 6, of BCC is how much? 8. Whereas in the close packing structures for HCP, for CCP or FCC, small FCC, for all these three, coordination number is 12. The sharing of atoms at corner, 8 unit cells are shared, at edge one sphere is shared by 4 atoms, at body center no sharing, that means 1 is equal to 1. At face center, one sphere is shared by 2 adjacent unit cells. These are some of the important points one has to remember during the competitive examinations. So let us have a look on the objective questions. In JEE Mains and NEET, beautiful questions are being asking on this solid state. Let us have some examples. Dear students, here is a problem. This was given in AIEEE 2010. An ionic compound has a unit cell containing of A ions at the corners of a cube. A ions are present at corners of a cube. I am drawing the cubic structure. At corners, how many corners are present? Total 8 corners. So, A ions are at the corners of a cube and B ions on the center of the faces. Center of the face. How many faces in a cube? 6. Here B atoms are present. Based on that, what is the formula of the compound? Now, A atoms, since they are present, 8 A atoms are present. Each A atom is shared by 8 other unit cells. So, 8 into 1 by 8. So, number of atoms of A is equal to 1. B atoms are present where? At the face centers. So, B, front and back. Total 6 B atoms. 6 into, at face center, 2 unit cells are sharing 1 atom. So, 3. So, empirical formula of the compound now 1A and 3B. Now, answer is AB3. This question was given in a IIT, previous IIT. The question is, if nickel oxide has the formula Ni0.98O, nickel oxide has the formula NiO, Ni is having 0.98 fraction. Then what fraction of nickel exists as Na+3? Options are like this. How we have to solve? Basically, this question belongs to the topic imperfection in the solids. That means metal deficiency defect. Here, Ni atoms are 0.98, oxygen atom is 1. If we assume there are 100 oxygen atoms, then 98 will be nickel ions. In this imperfection in this solid is because of the existence of Ni+3 ion in the place of Ni+2. Suppose X number of Ni+3 ions are present, then 98 minus X number of Ni+2 ions are present. Now, if we equalize the charge present on total nickel ions and total oxygen ions, 3 charge Ni+2 ions are X number plus dipositive ions, charge is here, dipositive ions are 98 minus X. This is the total positive charge on the cations. That will be equalized to 100 into negative charge on the oxygen. This becomes 200. 3x plus 196 minus 2x is equal to 100. X plus 196 is equal to 100. X is equal to 200 minus 196, that is called 4%. So, answer is third option.